So, let's see. There we go. So, back to recording, and then I have to watch like a hawk to see that the red light doesn't come out so that the people at home don't get it. Alright, so as I was just saying, because p squared is equal to a cubed doesn't have the mass in it, the mass of the planet doesn't affect the orbital period. Yes?
Can you briefly describe the element of falsification or falsification?
Falsification, yeah. So for a hypothesis to be scientific, it has to be falsifiable. Sometimes that surprises people. So falsifiable just means it has to be possible to do an experiment or to conduct observations that could prove the hypothesis is false. And sometimes that surprises people because they think, well, don't scientists want to prove that things are true? Yes, we would like to do that, but unfortunately, it's impossible to prove beyond any possible doubt that something is true. You can prove it beyond a reasonable doubt, but like in a court of law, reasonable doubt doesn't mean no possible doubt. It just means it's really very unreasonable to doubt it. But strictly speaking, we can't prove that a hypothesis is true, but we can prove that it's false. And an example I gave was, for example, if you take the force of gravity in Newton's theory, gmm over distance squared. Well, to show that that held in every possible case, you'd need to try every combination of masses and every possible distance between them. Well, how many different combinations of masses and distances between them could there be? And literally an infinite number of them. It takes a long time to test an infinite number of possibilities. Nobody has that kind of time on their hands, so we just test lots and lots of cases, and if it always works, we become more and more confident that it really is correct. But on the other hand, you know, we can't prove that there isn't some funny combination where for some weird reason it doesn't work. Everybody would be shocked. Physicists everywhere would just give up and go to a bar if that happened. But we're very confident that that wouldn't happen. We can't know for sure, though. On the other hand, all it takes is one good observation that, or experiment that others could repeat to show that something is false. It only takes one observation that's repeatable to show that something is false. Yes?
Can you just repeat what the diurnal motion is?
Diurnal motion, I don't think I ever said it once, but I'm sure I've said it before. But in other words, I'm not repeating it here.
Repeat it for your life.
Okay, all right, yes. Diurnal motion simply refers to the apparent motion of the celestial sphere around us. In other words, the Earth is actually what's turning, but it looks like the sky is turning around us. That's called the diurnal motion. So things rise and set, unless they're circumpolar. That's diurnal motion. Yes?
An annular eclipse has the moon slightly smaller in the sky than the sun.
Correct.
So does that imply that the moon does not have a completely circular orbit?
Correct. The moon does not have a completely circular orbit, right? Which is why the moon delights in making us sick by pulling this stunt. Every month I shake my fist at the moon because it's laughing at me because it's doing this. This is a computer simulation of one full cycle of phases, and so it's a synodic month, and the fact that the moon's orbit isn't perfectly circular means sometimes it's going around us a little faster than it's spinning on its axis and vice versa, so we don't see exactly the same half of it all the time. It nods back and forth. That's called vibration, and its apparent size changes a bit because it's bigger when it's closer to us, it looks smaller when it's further from us. So no, the moon's orbit is not perfectly circular. And so if a total eclipse happens when the moon is relatively far from us, it may not be quite big enough in our sky to cover the sun. And then we get an annular eclipse. But if the eclipse happens when the moon is relatively close to us in its orbit, then we get a total eclipse. The eclipse I tried to see, son of a fracking dork, back in 2009, was going to be great because it was happening near perigee, where the moon is closest to us in its orbit. And so that makes it relatively large in the sky compared to the sun, which would help give us last one.
What was the name of the point where this moon is closest?
Perigee. Yeah, so peri and apo are orbits. So if you're close to the sun and far from the sun, perihelion, aphelion. If you're near or far from the earth, perigee, apogee. Yeah. So you got your G, you got your heliopause. Yes?
But for perihelion and
Aphelion.
we
Yes.
talked about that with, not with the planets, because they're mostly circular, right?
So the planets' orbits do in fact have perihelion and aphelion, but it's not a big difference.
Yeah.
Yeah, because they're not quite circular orbits. They're not quite circular orbits, but Earth has its perihelion in January and its aphelion in July.
So we talked about like Katie's comment, how it's.
Yeah, so it's got a very dramatic perihelion aphelion. Yeah, yeah, and actually, yeah, that was the other thing is so the eclipse I tried to see was also in July. That was the other piece of it. So Earth was near aphelion and the Moon was near perigee. So the Moon was about as big as it can look, and the Sun was about as small as it can look. And that's the things you need to make the eclipse last as long as possible, because it'll do a better job of covering the Sun that way. Now, if the frickin' fracking, blinking black clouds hadn't gotten in the way, I'd actually be a happy person now, but instead I'm bitter.
So when you see a real fall eclipse, you'll feel better.
Then I'll finally be able to enjoy life again. Until then, every morning I get up and spit because I'm so angry that I didn't see that. I'm exaggerating just a little bit, but I'm still kind of upset by it actually. That was annoying. Yes.
One last thing.
Yeah.
Can you explain the difference between spring tides and neap tides?
Yeah, spring tides and neap tides. So, yeah, let me pull that up here. Where'd they go? Let's see. I thought I had that on my slides, but I do not have that here. Or is it, maybe it's chapter 3. I can easily forget which darn chapter it is.
Chapter 4.
No, it's not a chapter 7.
Chapter 4.
Chapter 4.
Is it chapter 4? Maybe I did not have it on here. I can still explain it, but yeah, I thought I had it in here. Maybe I forgot to upload the late or something. I don't know. But in any case, so tides are caused by the fact that the sun and the moon, their gravity isn't completely uniform across the sphere of the Earth because obviously one side of the Earth is closer to the moon than the other side, and closer to the sun than the other side. So the sun's and the moon's gravity are a little stronger on the side facing them, a little weaker on the side facing away from them. And the net effect of that is to raise tides. So the sun and the moon by themselves would raise tides. So if you just had the moon, acting on the Earth, then just by itself, the moon, and these are greatly exaggerated, as anybody who lives near shore knows, you're not covered by, hundreds of miles of water at high tide, thank goodness. But in any case, there's high tides on the line to the body causing them. So there's a high tide on the side of Earth facing the moon, also on the side of Earth facing away from the moon, and there's low tides 90 degrees away from that in both directions. And the sun also raises tides, but they're not as big as the tides raised by the moon because the moon is closer to us, and that means the difference in the strength of its gravity is greater across the body of the Earth than for the sun. They're both raising tides, and what that means is that if we're near new moon or full moon, the moon and the sun are both pulling together in the same direction, and their tides reinforce one another, and those are called spring tides. Neap tides are when the moon is at first quarter or third quarter, so that it's pulling at right angles to the sun, and their tides, basically the lunar high tide and the solar low tide are overlapping one another instead of the high tides overlapping one another. And so those are weaker tides as a result of that. So the strength of the tides is tied with the phase of the moon. The strongest tides are at new moon and full moon, and the weakest tides are at the quarters, first quarter moon and third quarter moon. And anybody who lives near a shore can definitely notice that correlation between the phase of the moon and the strength of the tides. Yep.
So,
Yes?
so new moon and full moon are spring tides?
Yeah, that gives you the spring tides. Yep. I kind of remember that by thinking, wow, the water is really trying to spring out when that happens, so to speak, right? And then the other ones, I don't know. The tides are saying, neep, if you know any Monty Python.
They're not gonna say,
Yes,
do they want
the
strawberries?
tides that say neep, right?
Then what do they want? Does seaweed kelps?
That would
for
be,
strawberries?
sure, why not, yes.
Oh, what? Neat.
Yes, I think, did you have a question?
I was wondering, why do some places have marginalized tides?
So it's really complicated, but so basically it has to do with the shoreline and how even like under the surface, do you have like a bowl shape there? Do you have a narrow confluence in a river there? Things like that. So it has to do with the shape of the shoreline, and it's not at all simple.
Okay.
Yeah, it's not at all simple. Yes,
This might be a dumb question, but
I doubt it.
why exactly do scientists prefer to find the simplest explanation?
Oh my God, I can't believe you asked such a perfectly good question. Yeah, why do we prefer the simplest explanation? That's actually a profound question, seriously, because on one level you have to kind of get philosophical and say, well, why does this work? But it tends to work. The idea with Occam's razor, preferring the simplest explanation, one is just in practical terms, right? In other words, another way to describe Occam's razor goes by the acronym of KISS. Have you ever heard that before? Keep it simple, stupid. So, in other words, just in practical terms, if you have some really complicated explanation and some simple explanation, and they both do an equally good job of explaining what you're trying to explain, choose the easier explanation, right? That's just common sense, right? Don't multiply hypotheses, as I think William of Ockham himself might have said it. But then, it appears to actually work in that, in the history of science, typically it's been found that the simplest explanation is the one that ends up being the best explanation in terms of being also the most correct, being able to have more done with it than more complicated explanations do. So it's partly it's a combination of, it just makes sense to choose a simple explanation over a complicated one if they both do an equally good job of explaining the results. And then, for reasons that are not fully understood, I would say, it works, basically. It is fruitful to try to keep your explanations as simple as possible in trying to come up with good theoretical explanations.
I have another question.
Go for it.
Why does the sun appear to move along the ecliptic over the course of the year?
Because Earth is going around the sun.
Okay.
And so the idea is that what we're really seeing as the sun appears to move around the ecliptic is the fact that Earth is going around the sun, and that causes the sun to look like it's in front of different things over the course of the year. So, in other words, so in other words, here's Earth going around the sun. Where we see the sun corresponds to draw a line from Earth to the sun, keep it going, and see what stars it's in front of. And as we orbit the sun, it appears in front of different stars. Just like as I orbit you, your head looks like it's in front of different things depending on where I am. And so if I circled all the way around you, and then I made a plot of where your head looked over the course of my orbit, it would trace a circle on my sky, so to speak. And that's what we call the ecliptic in the case of the sun.
So is that the same with constellations being visible in different places? in the sky?
It's related to it. So here is Earth on February 21st. If I draw a line through the sun from Earth, it lands in Aquarius, the stars of Aquarius. So, on February 21st, we say the sun is in the constellation Aquarius, meaning really it's in front of the stars of the constellation Aquarius. So, on February 21st, am I going to have a good view of the constellation Aquarius? No, because it's up during the day because the sun's in front of it. On the other hand, the constellation Leo is on the other side of the sky from the sun on February 21st. So I get a great view of Leo because it's rising when the sun is setting, pretty much. So at midnight, when the sun's way down, Leo's way up, 180 degrees away from it. So February, great view of the constellation Leo. On the other hand, 6 months later in August, oh, the sun's in Leo. I can't see Leo anymore. Oh, but wait, Aquarius is on the other side of the sky from the sun. So in August, great view of Aquarius, but I can't see Leo. So basically, we get a good view at night of the constellations, which are not in the direction that the sun is. But that changes over the course of the year because the direction of the sun keeps changing as we orbit. Yes?
Does Earth orbit speed like faster or slower throughout different times of the year?
It does because of the fact that we know that a planet moves faster when it's close to the sun, slower when it's further from the sun. The sun is closest to us, we're better to say, we're closest to the sun in January, furthest in July. So Earth is moving faster around the sun in January, slowest around the sun in July. And for that reason, winter is shorter than the other seasons, although it sure doesn't feel like it this year. But strictly speaking, even though it turns out that we've canceled the vernal equinox this year, which is not going to happen. There's never going to be spring this year. It's going to be freezing all year long. I've decided this. But nevertheless, winter is shorter because Earth is moving faster during winter. And that's why we picked a winter month to chop off a few days. That's why February is 28 days, because we needed to make one of the winter months shorter, since winter is shorter in length than the other seasons, and February is the one that got the axe. Yes?
Could you, I don't know if you went over this earlier, but could you kind of like talk about how to navigate the celestial globe? Like, are we going to have to do something like that on the test? Where, like,
So I could show you some photographs that correspond to what you did on those exercises, and based on those photographs I could ask you questions. So I think the thing to do is to look over those solutions that I posted for it, and even, you know, if you're finding that the pictures in there are not helpful enough, grab a celestial globe out of the library since they're on reserve, and even, like, you know, look at that while you're going through the solutions. But that's the best way to do that, is to look through those, and if necessary, have a globe in your hands so that you can see how that works. It's way too much to do right now, right? It's just but yeah, look through those again.
okay. Well, then could you also kind of go through Kepler's second law again?
Yeah,
If you
so
haven't done it.
it turns out I didn't. Kepler's second law is the one that says the line from a planet to the sun sweeps out in where is equal areas in equal times. Right, so the line from the planet to the sun sweeps out equal areas in equal times. So it's the law of equal areas. And if the times are different, are the areas the same? No, unequal areas in unequal times too. If the area is twice as big, it takes twice as long to sweep it, and so forth. So here's the illustration of the planet going around the sun. And so if these two areas are equal, and they are, it was drawn to make them equal, then it would take the planet the same amount of time to go between the first and second edges of that area that is swept out. So that's the big picture with it, is equal areas get swept out in equal time. Not equal distances, but equal areas. So the planet has to go farther in the same amount of time when it's close to the sun, because the line got shorter, so to sweep out the same area, the arc has to get bigger in order to compensate. So Kepler's second law implies that a planet moves faster when it's closer to the sun, slower when it's farther from the sun. And there were lecture tutorials that dealt with that idea. So you might want to look over those. See you later. Yes?
Can you explain what azimuth is?
Azimuth, So azimuth is direction away from due north measured to the east. So on the celestial globes, azimuth is what is indicated on the horizon ring, where it started at 0 on due north and then said 90 for due east, 180 for due west, 180 for due south, 270 for due west. And so here is a representation of somebody standing and pointing at something. So azimuth is measured to the east away from due north. So by definition, due north is 0, and you measure to the east, so 90 degrees away is due east, 90 more degrees is due south, so that's an azimuth of 180. 90 more degrees is due west, that's an azimuth of 270. Then back around to 0 again, 359, 0 when you get to due north again. And I also mentioned the fun fact that that's how airport runways are numbered. That you take the direction, you take the azimuth the plane is flying in and divide it by 10, and that's the number of the runway. So a plane which is flying at azimuth 270, which would be towards the 220, which would be towards the southwest, is said to be landing on runway 22 as a result of that. Yes?
Can you just go over the zodiac?
Yeah, so the zodiac are just the constellations that include the ecliptic. So the ecliptic's the circle on the sky. I shouldn't quite say this. The zodiacal constellations are the one that the ecliptic passes through. There's 13 of them. Classically, there's 12, but the constellation Ophiuchus in the modern boundaries also has part of the ecliptic going through it. And the zodiac is a band. There's no strict definition, but it's often said to be a band that's about 18 degrees wide, north and south of the ecliptic, because all the planets and moon and so forth are always found within that band because of this alignment of orbital planes that we're starting to talk about. And so, the zodiac is that region of the sky where the sun, moon, planets, and so forth are found, and it's near the ecliptic.
Are we going to have to know the constellations that are in there?
No. I think most people know a lot of them. You know, Gemini, Scorpius, Sagittarius, Leo, and so on and so forth. The 12 BS astrological signs plus Ophiuchus. And there's a couple of things like astrologers say Scorpio, but the constellation's name is actually Scorpius. Yes?
Can you go over the precision of the equinoxes?
No, because you're wearing a Patriots sweatshirt. So, precession of the equinoxes is, it just refers to the fact that Earth's axis of rotation is not staying pointed in the same direction. And so that's how we were talking about how the Earth is kind of wobbling like a top. And it's called precession of the equinox. So the precession is this slow wobbling motion like a top does. And it's called precession of equinoxes because of the fact that, remember we were talking before about the sidereal year and the tropical year. The locations of the equinoxes are moving around Earth's orbit every 26,000 years because of that wobbling of the Earth's direction of rotation. So where the Earth is in its orbit at an equinox is going to depend on what direction in space the axis is pointing in. So it's called precession of the equinoxes because of that. But it could just as well be called precession of the solstices.
And that's written that when it says for the pole star, that's for the same as because every 26,000 years the pole star changes.
It's constantly shifting. In other words, the direction that the north celestial pole is in is moving on. It's actually not quite a circle because there's an additional wobble superimposed on this. but it's moving around a circle on the sky with a period of 26,000 years, roughly. So right now it happens to be near Polaris, but at other times, like in 88,000, it'll be over here,
Okay.
and so forth. So Polaris won't always be the pole star.
You said it's not staying, perception is when it's not, because it's not staying in the same location in the sky.
Yeah, so precession is the fact that Earth's axis of rotation is slowly wobbling around like a top does. Have you seen a top wobbling before? Yeah, so Earth is doing that too, only it takes 26,000 years for one wobble. So it's very small by human standards. The Earth, of course, spins on its axis many, many times for one wobble. It's a much more gradual wobble than a top that you can play with does. Yes?
Can you kind of talk about a little about like how you determine what phase the moon is based on, or like how to determine what time, like we were doing the moon thing on
Right.
the computer. I still don't understand like how if it's at noon, what phase of the moon is it and stuff like that.
So it's not enough to just say it's noon. You have to have another piece of information,
Like a date.
for example. Right? So, no, not a date. You have to know some, so essentially, the phase of the moon depends on where it is with respect to the sun in the sky. It's all about where is the moon in its orbit around the Earth. So, if, there's lots of different questions I could ask, but for example, if we said something like, it is noon and the moon is rising, what phase is it? That would be an example, right? Okay? Then, if it's noon and the moon is rising, where's the sun in the sky? Yeah, is it straight overhead?
Yeah.
No, remember that's only if you're within the tropics can the sun ever be straight overhead. Right, we're too far north for the moon to ever be straight over our heads, but it is high in the sky in our northern locale. At noon, is the sun in the northern sky or in the southern sky? It's in the southern sky from our location, because if this direction is south and this direction is north, the north celestial pole sitting above the horizon, south celestial pole below the horizon. So things turn around the north celestial pole over the course of the day. So the sun rises up and to the right and climbs into the southern sky. And around noon, the sun is on the meridian, the north-south circle. So it's high in the sky in the south at noon. And so if we do the moon phase wheel, and that's something where you should really go through all those exercises. And if you've done that and you're stuck, you should come see me about it. I'm still around this evening, but with that moon phase wheel would be one way to do it. Here is 6 p.m., 6 a.m., noon, and midnight. And for the northern hemisphere, we would put south up to represent that around noon the sun is high in the south, north down because at midnight the sun is hidden in the north, and then here would be west, here would be east. If it's noon, there's the sun high in the sky in the south. We're in the middle here. It's noon and the moon is rising, so where do I draw the moon here?
East.
East, right? Because things rise in the east. So I would draw the moon in the east, and then based on that, I can say, okay, what's the angle from the sun to the moon? 90 degrees. So there's a 90-degree angle from the sun to the moon. So moon is 90 degrees east of the sun, because I have to go towards the east, towards the eastern horizon from the sun, which is above the horizon, to get towards the moon. So 90 degrees says what phase? What phase is the moon 90 degrees from the sun? Crescent, gibbous, quarter, full, new. What's 90 degrees from the sun? Now, quarter phases, right? Quarter phases are the ones that are 90 degrees away. So this is a quarter phase, and it's east of the sun. So is the moon waxing or is it waning if it is east of the sun? It's waxing if it's east of the sun. It's waxing if it's east of the sun. Because the moon orbits Earth towards the east. So imagine you go out at sunset and you see the moon. Okay, for me to be able to see the moon at sunset, it has to be east of the sun, right? Because it has to be, I'm swinging from the sun on the western horizon to the east to see the moon. So the moon is orbiting us from west to east. So the next night, is the moon going to look closer to the sun in the sky or further from the sun in the sky if it's orbiting to the east? Further. It's going to be further from the sun in the sky. Will that make the phase open up or close down? It'll open up because as it's getting further from the sun in the sky, we're seeing more and more of the lit face until it gets opposite the sun, in which case we'd be seeing the full phase of the moon. So waxing phases are east of the sun because the moon is getting further and further east, opening up the phase, so to speak. So the phase of the moon must be waxing quarter, but if it's waxing quarter, is that first or third quarter? You already said it. That's first quarter. So this would be a first quarter phase in that situation. So if you can locate both the sun and the moon on the moon phase wheel, so to speak, then the angle tells you crescent, gibbous, full, etc., right? Less than 90 degrees, what phase is that? Leave out waxing and waning. Less than 90 degrees, an acute angle. That's a crescent. More than 90 degrees. Gibbous, right? 90 degrees, we've already said, is quarter. 180 degrees. Full, 0 degrees. New for 0 degrees. So the angle tells you the type of phase it is in terms of quarter, crescent, gibbous, all that kind of stuff. And then if it's east of the sun, which on the moon phase wheel means that the moon is counterclockwise away from the sun on the wheel, then that's a waxing phase. And if it's west of the sun, Cowboy Wayne rode out west, that's a waning phase.
Wait, how do we know the moon was east again?
Because here I'm pointing at the sun, and I'm moving, to get to the moon, I'm going towards the eastern horizon. In other words, if I'm pointing, here's the sun, high in the sky in the south, the moon is rising over there in the east. So to get to the moon from the sun, I'm arcing towards the eastern horizon. And that means I'm arcing eastward. That's what it means to say that the moon is east of the sun, is if I point to the sun, if to get to the moon, when the sun's above the horizon, I have to arc my arm towards the eastern horizon, then the moon is east of the sun in the sky. If I had to arc towards the western horizon to get to the moon, then the moon would be west of the sun in the sky. So it's an angle on the sky which can be either to the east or to the west, depending on, are you moving towards the eastern horizon away from the sun to get to the moon, or towards the western horizon?
So if the sun was at midnight, would be moving west to get to the moon?
So, if the sun, you mean, yeah, I mean, in other words, if we turn this into, it's midnight and the moon is rising, then the moon would be west of the sun, yes. Then the moon would be west of the sun, and it wouldn't be first quarter, it'd be third quarter in that situation. Yep.
Okay.
Yeah, third quarter rises at midnight, first quarter rises at noon. Yes?
What's the difference between a mean solar day and a sidereal day?
So the sidereal day, so your book actually gives a slightly incorrect definition of the sidereal day. The book says sidereal day is one turn of the Earth's axis with respect, one turn of the Earth around its axis with respect to the distant stars. That's not the strict definition, although it's almost right. Strict definition is the sidereal day is the time between successive meridian transits of the vernal equinox. So it's the time for the vernal equinox to go from the meridian all the way around and back to the meridian again. So if there was no precession, that would be the same as the sidereal day. That would be the same it took for a star to go from the meridian all the way back to the meridian. So, to an awfully good approximation, the sidereal day is how long it takes the Earth to turn once on its axis with respect to the distant stars. The mean solar day is the average amount of time it takes the Sun to go from the meridian back to the meridian.
And since the Earth is moving around this axis, it's turning more.
That's right. So it's similar to the fact that the sidereal month and the synodic month aren't quite the same. The mean solar day is analogous to the synodic month, where if I'm the Earth, okay, here's my nose pointing at you, the Sun, okay, so if I wasn't going around the Sun, then when I turn 360 degrees, my nose is facing the Sun again. Now, in fact, though, at the same time Earth is spinning on its axis, it's also going around the Sun, so after I turn 360 degrees, my nose isn't yet pointed at the Sun again. I have to turn a little more to point my nose at the Sun again. So the Earth has to turn through a little bit of extra angle to get the Sun back lined up with the meridian again. So the mean solar day, the apparent solar day is always longer than the sidereal day. The length of the apparent solar day changes over the course of the year because Earth isn't going at a constant speed around the Sun, and because the Sun is going north and south of the celestial equator at a tilt, and it's the Sun's right ascension that really controls when it's on the meridian and so forth. So we have to have a mean solar day to use with our clocks, because if we use the position of the Sun, that wouldn't keep steady time. So we make an average solar day, the mean solar day, as the basis for civil timekeeping.
I'm looking at my review sheet to see if I have any questions.
Okay. Maybe what we should do for you, Rachel, since you weren't able to be here at the start, is you can come and ask me more questions or something.
The doors were locked.
Oh.
I was standing in the doorways for 15 minutes begging and screaming.
Yeah, unfortunately the doors lock at like 6 or 7 p.m. or something like that, and so I'm kind of stuck in terms of, I keep looking for people, but after a while I just got to start having a review session. Yeah. So then you need to have a friend who's here to keep you text or something.
Yeah.
Say, let me in, let me in.
I was here at 8 though.
Were you really? Yeah, okay. Well, we started at 7, but you were trying to get here, yeah.
I thought it started at...
No, it was at 7, yeah.
Are you kidding?
No.
No wonder there was not many people here.
Yeah, that's right. Yeah, there was a lot more people.
I thought we said in class it was going to start at 8.
No, 7.
It was written on the blackboard that said 7.
Mm-hmm. Yeah, so somebody had said, could we do it at 8? And I said, and so, but yeah, so.
Oh.
Right. I think somebody might have said, well, I could come at 8, and I said, well, no, let's try to start it at 7 because I'm going to put it on YouTube and stuff like that. Yeah.
I'm
So
sorry.
I am going to put it on YouTube.
Okay, yeah.
If you want to ask me some questions or something, you can do that.
Can I send
But this
you-
way I can get. What's that?
Can I send you emails?
You can. Now, if it's something that it would take me War and Peace to explain.
Yeah, I'll try to make sure it's okay.
Right, and also I would say, watch the review session. Now, it'll take a while for it to
Well,
get.
yeah, I was going to watch that first.
Yeah,
and
watch
then
it,
I
and then
have
if there's
questions.
something that's not explained there,
Okay.
send me an email, and I will do my best to answer it, as long as I wouldn't have to stay until 3 in the morning to answer it,
Okay,
Yeah.
All right. I didn't know, or I wouldn't have even come at 8 o'clock.
Yeah, okay.
I could have been here at 7. I thought it started at 8.
Whoops, okay, yeah.
Sorry, that was my bad.
All right, and I said, just saw you said an email.
Yeah.
How do we get into Science Center? Yep, certainly.